Welcome, everyone. Welcome to our virtual science and a movie experience here featuring Secrets of the Universe. I'm Gretchen Walker, and I'm the Vice President for Learning at the Tech Interactive, and I'm so excited to be able to bring you to this event today because it was a film on this very topic that I saw when I was 15, or at least where this topic was 35 years ago, that turned me on to science and got me to study astrophysics in college. So I'm so excited for today's event. But before we get started, a couple of housekeeping items for you all. First off, you'll notice if you look up on the corner of your screen that today's event is being recorded, which means if you have friends or family or other people who you really wish had seen this, you'll be able to share the link with them later. We also would like to take a minute to really thank the supporters of the Tech Interactive, especially you, our members. It's because of your generosity during this time that we've been able to provide programming, not just for you, but for teachers and students as they try to tackle this very difficult school year. So thank you very much for your support. Be sure to keep a lookout for our member newsletter to make sure that you know when we have upcoming other webinars and other activities for members. We have some great ones coming up soon that you'll be able to see announced through the newsletter. So we're going to go ahead and get started with the program. We will be taking any questions that you have, as we're hoping this is going to be a highly interactive program, through the Q&A or the chat function. We will be monitoring both of those throughout the presentation. And with that, I'm going to introduce our guests. Born in Mexico City, Professor Manuel Calderón de la Barca Sánchez is the son of a tenacious father who believed in the value of education and a mother who encouraged him to spread his wings and fly. As a child, Manuel wanted to be a fighter and loved video games and computers. But as he grew up, he discovered that he loved math and that it was the secret language that could help decode the universe for you. Today, Manuel is a professor and researcher with the UC Davis Physics Department, where he's seeking to understand the universe through a field called quantum chromodynamics. More on that in just a bit. Through his work, Manuel and his team seek to discover the secrets of the universe, and he's here today to share some of those secrets with us. Thank you and welcome, Manuel.
Thanks, Gretchen. Yeah, it's a pleasure to be here.
Also joining us today is the film's director, Stephen Lowe. Stephen is recognized by audiences and peers as one of the world's foremost large format filmmakers. His creative vision, his storytelling ability, his commitment to cinematic innovation have yielded an extraordinary body of work enjoyed by audiences around the world. His career spans more than 3 decades and includes 17 giant screen films and award-winning work for television. And we're actually going to drop a link in the chat to send you to more of Stephen Lowe's bio, because I know we have a lot of IMAX junkies in our membership pool who would like to know more about Stephen. So Manuel, can you tell us a little bit about how this program is going to run today?
Sure, thanks, Gretchen. So what we're hoping is to make sure that that everybody gets a chance to ask questions, and we have a unique opportunity here that you have both Stephen and myself to answer questions about the movie. So what we're planning to do is I'll show some clips of the movie. So I'll just briefly introduce each of the clips. They're all about a minute or so, some a little bit less, some a little bit more. And we can then use the clips as a springboard for discussion. So we can talk about anything that you might want, like, you know, why did we decide to shoot at CERN? Why CERN? What is CERN? What are the accelerators? Any questions that might pop up in your head as you start seeing the clips, just drop them in the Q&A or the chat, and then we'll try to address them. But the goal here is to be as interactive as possible. Like, we're here to try to help answer any questions and clarify what are we doing, at least when in some of the experiments that we focused in the film, when we smash these nuclei together. And that's what the film is about, trying to tell that one story. And so that's kind of how we want to run it. Anything else that we want to do before we start going towards the clips, Gretchen?
I'm just going to ask if somebody out in our audience can go either to the chat or the Q&A and type a test question for us, just so we can make sure that that stuff is coming through so that we don't miss any of your questions. So particularly if I've got any tech staff listening in on the webinar, drop me a question. Aha, yes, thank you. I can see questions appearing. in both places. Thank you very much. All right, with that, Manuel, I think we can get started.
All right, so let me share my screen with the slides. And the very first, oh, give me 1 second, because I think I didn't actually share my audio, which is something that I need to do since we want to hear. Oh yeah, it is click to share the audio, so that we can actually hear the various clips. So let me go now to full screen mode. And as I mentioned, so the film is called Secrets of the Universe, and Stephen and I'll be more than happy to answer questions about it. So the first clip that I want to show, when we're thinking about the movie itself, Stephen was very clear to me that, you know, we needed to have a story that, you know, as scientists, we always start, you know, when we had the dialogue as to what we're doing at CERN, we talked for many hours as to what we're actually doing. But Stephen was very clear that, okay, we need to tell a story. And one of the stories that kind of like the unifying thread that Stephen thought would be a good one to take is to focus on kind of something that's familiar to many people, but then that we can use it to go even deeper. And so what we thought would be a good idea was the atom itself, because the atom is something that is something that we can learn about in many science classes in school when we talk about like what the nature of matter is. And it's something that goes to some of the questions that many of us ask when we are kids. When we think about what we are made of, and if we then think about what makes that makes us. So that's kind of what the first clip introduces, that idea. And then we can chat about that and how this idea has been something that we've been essentially asking for thousands of years. So, and we're still essentially unraveling that idea. So let me share the first clip, which is basically the first sequence of the movie.
It was once thought that all things were composed of water, air, soil, and fire. But in the 5th century BC, the Greek philosopher Democritus proposed that all matter must be composed of something invisible. Long before the dawn of modern science, this speculation remains among the greatest insights of the human mind. The ancient Greeks called these tiny particles atoms. But where did they come from? And how did they come to exist? It is the ultimate question.
So it's an exciting start there. And I think a question that jumps to mind immediately for me, Manuel, is, so the name of your field is fascinating, the thermo-quantum dynamics. Can you talk a little bit about what that is? And then I see we have a ton of questions coming in about what a particle collider is as well.
Sure. So yeah, the field that I study is called quantum chromodynamics, or at least the theory of the strong interaction is called quantum chromodynamics. And when we get to some of the sequences that go deeper into the atom, we'll talk a little bit more about why. So as we see, basically, even from this sequence, a lot of what we borrow when we're discovering new things, we have to invent names for them. And even the word atom, which right now sounds familiar, at some point it was an invented word. And it comes from the Greek atomos, which means indivisible, unbreakable. And just as we've borrowed from the Greeks basically since then, chromodynamics is also borrowing from Greek. Chromo in Greek means color. And I'll talk a little bit about that when we get to a sequence where we go into when we zoom inside the atom. Because we've found in the last 40 years or so that the atom, as the Greeks thought, is not really unbreakable in the sense that they wanted. In some sense, it is the smallest piece of a given chunk of matter. So for example, if we think of gold, if we want to say like, can we keep cutting and cutting and cutting a piece of gold until it's no longer gold? In that sense, the atom is the smallest piece of gold we can have. But it is not unbreakable in the sense that the Greeks wanted. Like, can you find something that is smaller and smaller and smaller to the point that you can't break it anymore, and you use that to build everything else? So when we get to that, we see that particles that are, at least as far as we can tell, that ideal are new particles. We again had to come up with a name for them. We call them quarks. And these quarks carry a new kind of charge that behaves in a very different way than electromagnetism. And so we had to invent a new name for it. And we realized that in order to make a neutral object, you need 3 kinds of that same charge. Because of that, because of those 3 pieces of charge that combine to make something neutral, something that we had never seen before, we came up with the idea, well, that sounds a little bit like what we do when we combine primary colors. When we combine primary colors, we can get something neutral. And it just helps our human mind remember something that is new about a new force of nature. And so we use that mnemonic, primary colors combine in 3 parts to make something neutral, to give the name to this force, not because these particles are actually color in the sense of how we see color, but because of how primary colors combine. And so that's why it's called chromodynamics. And so these new particles, again, we had to invent a name for them. We invented the name quark, and we invented the color charge to describe how they interact. So we call this theory chromodynamics, the dynamics of particles that carry color. But even, it's just a whimsical name, if you want, to try to describe something that we didn't even know existed until about 40, 50 years ago. So that's part of the fun, that in physics, we're still discovering things about our universe. And so as we were zooming in and zooming in, we were able to find things that we didn't know, that no one knew before. At some point, the atom itself was a new concept. And now the quark is a relatively new concept. And maybe there will be new people that might be listening in now, that if they're young and they're about to go into a career in science, they might discover something new that then eventually will be something that then becomes a standard in terms of finding something new in our universe.
Great, thanks. Stephen, a question for you. What led you to want to make a film about the very, very, very small parts at the beginning of the universe?
Well, I'm kind of fascinated with the simplest things. As a filmmaker, especially IMAX, where you're so overwhelmed by the size of the screen. You're really always searching for the simplest way to explain something. And our audience is mostly children. I mean, they're the ones that make the choices to go to a film or not. And I thought, if I could put them in front of a beautiful atom that's just floating in the theater, and this is a 3D image as well, so that they actually come out into the theater, and they're very dynamic characters. And now this isn't a hydrogen. And my favorite atom is hydrogen. My dad used to remind me, if you're struggling with chemistry, always return to your friend hydrogen. And that I still found that with talking with Manuel, is I could still stand beside a hydrogen and atom and go in any direction. I could go out towards chemistry and the periodic table, and then out from there, biology and the ultimate silliness of economics. And in the other direction, I can go to physics right from that starting position. And it's hard to fund these films. Very, very difficult to do that. And to have the money from NSF in particular, to have the money where you actually go and build an atom, a really nice one. And it was just so much fun. And you're only seeing a tiny piece of that now because of that scale of it. And our computer graphics people, they got so excited with, because they, you know, used to be doing Hollywood nonsense all the time. And, you know, this is a chance to do some real science. And they really got into the rings and, you know, what an atom would look like if you could see it and that kind of stuff. So.
Actually, one of the things that I really like, let me share one picture. Let's see if you can see it here. Yeah. So these are actual mathematical shapes that you can calculate that come out of the theory of quantum mechanics that give us the various shapes that the electrons can take in their orbits around a hydrogen atom, for example. Mm-hmm. And the animators really did a good job of trying to really have some of that represented. So let me see if I can go back to some of those frames of the in that sequence where you can start to see some of that there. So you start seeing the various bulbs. So it's not just like you see the sphere, which is one of the possible configurations that the electrons can take, but you also see sort of these double bulbs and some of the other possible configurations. And they really tried to get to convey those shapes that even hydrogen, which is the simplest of all, depending on what electron levels you might have, the shapes might not necessarily be spherical. And so we don't necessarily go into the details, but we show the images there that are all based on that science.
Great, thank you, Manuel. We have a number of questions coming in on the Q&A in the chat, all about colliders. What are they? Where is CERN? What does it stand for? I think that sets you up well for your next clip.
Yes, I think I was going to say the same thing, because the very next clip is indeed about the collider. As you can read in the bottom of the slide, I tried to make sure, like, you know, there's there's lots of words that we use that are sometimes new and sometimes are invented to describe a new thing. But I always like to, as Stephen says, find the simplest way to explain something. So what is a collider? It's a thing that is able to break tiny things. That ultimately is what a collider is. We're trying to get to the smallest bits of matter possible. So that's what a collider is helping us do. So this is the sequence that kind of introduces the collider, and there will be several sequences to get into more of the details, but this is where we first just get an idea of the scale of the collider.
I'm back in Geneva for the next few weeks to work with the Large Hadron Collider. 27 kilometers around and buried on average 100 meters underground, it is the largest scientific instrument ever built. With it, we will seek to look back in time to the very beginnings of the universe.
So if I can go back a little bit. So you can get an idea of how big this thing is. Again, we said, you know, it's 27 kilometers around, something like 17 miles, 18 miles, something like that. We always like the idea of that this is, you know, a visual medium. So to get something that might be more familiar. So if you see at the top of the screen here, that's the Geneva airport. So these are the runways where, you know, 747s can land. So that maybe gives you also an idea of just the scale of how big this thing is. And the various, you know, patches of green and yellow that you see here, those are farms. The city of Geneva is out here, and there's various other towns all the way around. And the accelerator is big enough that part of the border between France and Switzerland essentially goes through the area of the ring. So some parts of the ring are in Switzerland and some parts of the ring are in France. So that's how massive and how big this thing is. And we'll eventually get into some of the clips that show what's happening at the very beginning, but ultimately the kind of the first answer to what's a particle collider is it's a machine that helps you smash particles and study what happens when you smash them. So get really deep into an atom and hopefully into a proton, which we know we can do, and then into the quarks themselves that make up those protons, that make up the atoms. So it's going smaller and smaller and smaller, as small as we can possibly do. So that's one of the ways in which you can describe a particle collider.
Manuel, we have a couple questions coming in about what the practical applications are, or if there are things that were discovered at CERN that impact the world in a more practical sense. Do you have anything to share on that front?
Sure. There's several answers to that. One of the things that I think is always important to think about regarding accelerators, for example, is that nowadays most of the world's accelerators, I think, one of my professors told me it was over 95%, it might be 99% at this point, of the world's accelerators are actually housed in hospitals or medical facilities. There's therapies that you can do using, for example, proton beams that are useful for basically zapping tumors. And so people are able to use those particle beams to very precisely reach regions even within our own bodies and attack some types of tumors that way. So there's a clear application that is benefiting our health. And this is just one end of the scale that is a kind of like a direct application of the accelerator technology itself. But on the other side, there's also just ancillary technologies that might be coming simply because you're doing the research that is pushing the envelopes of what you can do technologically. And perhaps one of the most famous, or at least biggest, not necessarily, I mean, not a lot of people know about it, but I think, once people know that this is, they're like, oh, this is where it started. CERN was the place where the World Wide Web was actually born. So when scientists in the early 90s needed to share data across, we're in universities housed all over the world, then we needed ways in which we could seamlessly interact no matter where we were, and we're, harness the power of the internet to do that. And so at CERN, the World Wide Web and hypertext and web browsers and things like that, that's where they were first developed. And nowadays, that's something that is ubiquitous, that you could find anywhere, and people don't necessarily even know that this actually started to help particle physicists communicate. So those are just two examples of technologies that basically are now everywhere. Some that can impact your health if you happen to have a tumor very directly, but just in everyday life, everybody uses the web nowadays, and that was started at CERN. So those are just two examples.
Great. I also see in the questions, we're asking a little bit more about how does a collider work, and if a collider is about breaking the boundaries down inside of atoms, does that mean that it's causing explosions, that things can explode?
So in some sense, yes, and in some sense, no. So we do collide particles, and basically when you look at the pictures, and we'll get to that in some of the sequences, they basically look indeed like explosions, but they're explosions at the particle level. In that we basically, from the energy in the collision, we can produce new states of matter, new particles that weren't there before, but that are allowed by the laws of physics. And so the outcome of that is that you get these, showers of particles flying out all over the place, essentially an explosion, but it's not an explosion in the way that we're used to saying, well, like, you take dynamite and you make it explode in a macroscopic way. It's really just particle by particle. And so the danger there is not so much that things are blowing up, but rather it's because the particles are flying out at high energies. It's a radiation type danger that you have. That's why when we run the collider, we don't have people inside the experimental zones. But we'll definitely get more to the, closer to that and show some of the sequences where we can kind of see the result, or at least in the film, we have some of the artists' imaginations as to what happens when the particles actually collide. But we can actually show when we get there, I'll show you some pictures of how the data actually looked like. So we can talk about that. And that was definitely one of the more interesting things to me, like that's when we were able to show some of that. And I remember talking with Stephen about like when would be a good time to show it, because indeed that is one of the kind of the climactic moments of the movie where you're able to show the particle collisions. And so we'll get to those kind of towards the very end, because those are the most interesting parts, I think.
Before you leave this image, there is a question that came in about, so is this actually in Geneva, and is that an issue at all? So
the city of Geneva, while we're on this image, the main kind of downtown area is just off the frame here. Let me see if we can kind of zoom back out a little bit, so you can kind of maybe see better. So this is the lake, Lac Clément, and so over here, so just off the frame, that's where the main downtown area is. That's where it kind of converges. So the main city of Geneva is over here, but you see that this is the city of Méran, and this is the main CERN site, right? Kind of like in this area here. So yeah, it's close to the city of Geneva, but the collider is buried deep underground. It's like 100 meters underground, and part of the reason why we put it underground is partly for safety reason, but also partly because that helps to shield the experiments from other noise, like cosmic rays. And so just to make the experiments work better, we basically build them underground. But that also helps to provide some margin of safety. And so, it's useful to have an international city like Geneva close by, because this is where essentially the entire world of particle physics converges. And so to be able to have easy access to an international airport is a very good thing. But yeah, in terms of whether there's any issues, in general, it's worked okay, but there have been some interesting things. Like, for example, in the early 90s, the Den collider that was housed in the same tunnel was having some issues. It would lose the beam periodically, and people didn't know why. And eventually, after trying to do correlations with the height of the water in the lake or the phases of the moon, they figured out that it was actually the trains, the high-speed trains, that were, when they were coming into the city of Geneva, they would create spikes in the power that would, send the particles off from their orbits by a tiny little bit, and then they would lose the beam. So they figured out that yes, that actually having the city can sometimes lead to some unexpected effects, like having the trains mess up your collider. But once they figured that out, they were able to correct for it, and then things kept working fine after that.
Great. All right. Well, why don't we move on to the next clip and get a look at what you actually do with the collider?
Yes. So in the next clip, we wanted to introduce the research that I do, which is studying what we sometimes call the primordial soup of quarks. And so we were introducing the idea that we wanted to study this strong interaction of protons and neutrons that exist deep within nuclei, because people thought when they first understood that this force existed at the nuclear level, that perhaps at the very beginning of the universe, that's what dominated the entire universe, that everything in the universe. Right now we see planets and stars and an empty space, but maybe close to the very beginning, everything was dominated by essentially just a soup of quarks. So that was the conjecture. And what my experiments are trying to do are to try to check to see whether that conjecture is true. So this is the clip that kind of introduces that idea.
One idea suggested we could simulate a moment in time when atoms had not yet formed. It would become one of the most ambitious scientific experiments ever undertaken. A journey to the most distant edge of the universe in both time and space. 14 billion years closer to the Big Bang. A moment long before our Earth and solar system were formed. A journey back to the quark-gluon epoch, a time and place too hot for even atoms to exist, where subatomic quarks were thought to be held together by a mysterious force. The strongest in the universe.
So yeah, in that clip, some of the things that I like are how we get to see things that when I was growing up were not necessarily well known. Now, in the last 20 years, so this number, for example, the fact that we know that the age of the universe is to me mind-blowing, and that we know quite a lot about the whole evolution of the universe. You know, basically from just a few microseconds, millions of a second from after the Big Bang up till now, that there are well-known physics processes and well-known you know, structures of how the galaxies formed, how the planets formed. So the fact that we are able to know that we have the diagram with such detail as to how the universe evolved through most of its life, to me is pretty mind-blowing. Because this is essentially a question that we've had for essentially all of humanity. And so that was definitely one of the things that I think we wanted to include in the movie. Because it's still, when I think about it, it still blows my mind.
I have something to say. Should I put up my hand?
Go ahead, Stephen, you're good.
It took us, Manuel and I had many long discussions about how to do this film, because physics, as you know, can be very complex. And a lot of people advised me that this film was just too hard to make because it's just too complicated. But at some point, I started listening to Manuel carefully, and I realized that CERN was about the simplest thing in the universe. And what better simple topic than the simplest thing in the universe? But it took a while for that to sink in. I'm not sure why, but this is literally the quarks from which formed the hydrogen that built the universe. I mean, it is the ultimate simple question, and what a great thing for a place for children to start their knowledge of science than this very plasma, if you will.
Yeah, we definitely had a lot of discussions around, okay, how are we gonna tell this story? And when Stephen said, like, yeah, we should just focus on the simplest thing, and you know, how can we make the simplest thing? How can we tell the story of the simplest, you know, going from the atom to its underlying simplicity? And then, I mean, we talked, because at the very beginning we were wondering, there's so many things that CERN does, that we explored several of the various discoveries that CERN had over the last few years. But as Stephen said, we needed to be able to tell a story that's understood by everyone. And so when we hit upon the you know, okay, when we're trying to understand the beginning of the universe itself, and how the very first state was, in some sense, pretty simple. It was a soup of quarks, and then everything that we know kind of came from that. Then
it's almost as if they built the CERN for our film. I mean, we could have looked at it that way. That's quite the budget for a film, isn't it? But
yes, we definitely took advantage of that.
Sorry, carry on.
Oh yeah, no. I think you can tell us, Gretchen, if there's any questions about it. We can also go to one of the next clips as well.
I think the questions that are in here will go better with your next clip. So go right ahead and head on to the next clip.
One idea.
Sure. So yeah, so then we wanted to also then, you know, introduce the idea of quarks. So we've just been talking about these quarks, but we wanted to also have that introduction in the film, because not everybody has the chance of like doing this interactive experience. But since we mentioned that, you know, we thought atoms are something that perhaps is going to be more familiar, protons perhaps as well, but quarks might not be. We did want to, you know, kind of guide people going smaller and smaller and smaller from the atoms down into the proton, down into the quark. And so that's what this sequence is about, where we first kind of are introduced to the notion of the quark.
Here at CERN, we study the tiniest particles in nature. The hydrogen atom is the simplest of all. It has an electron spinning around the outside. If you pass through the electron cloud, continuing towards the center, you would find a single proton. Inside are 3 quarks, held together with the strongest force in the universe. For us, understanding this force is the holy grail of physics.
So some of the questions that have appeared, Manuel, are about how were atoms formed to begin with? And what do we know about how the Big Bang happened?
That is indeed part of what the film is about. This is the first part of the question. How did atoms form to begin with? And as far as we can tell, and that's why we first start going into the quarks and talking about the quarks, and that in particle accelerators, as we were going smaller and smaller and smaller, around the 60s, we realized that the proton, which was one of the building blocks of an atom, itself was not an elementary particle, in that it had other building blocks. It had other tiny things inside it. And so this is something that we've only known since the 60s, which, regarding, our human history is the blink of an eye. And so we, the name for quarks came out in the late 60s. The theory that describes how these particles interact didn't come in until about the 70s. So that's the theory of quantum chromodynamics, which, as I mentioned, it came from this idea that we have the primary colors. And that's why I like this visual here, because this visual shows these quarks with 3 different colors. So even though we never mention chromodynamics or anything like that, we just give the idea that visually these quarks have something that is in 3 different kinds. One is blue, one is red, one is green. And that's still how a lot of physicists just kind of in the back of the mind think of how these quarks actually interact. That they have a particular kind of charge, and there are 3 of these kinds, and in order to make this big blob here, big for the purposes of the quarks, but small for the purpose of us, you have to have 3 of them to combine this kind of droplet that we call a proton. And the same thing happens for the neutron. You need 3 of them to make a neutron. And so the speculation started in the 80s that if we knew that the Big Bang existed, because that's something that we knew basically since the time of Hubble around the 30s or 40s, then this is a really interesting thing, because it's the marriage of 2 areas of physics that seem to talk about very disparate things. The astrophysicists, who look at the large scale of the universe, galaxies and clusters of galaxies and even beyond, and the particle physicists who are looking into the tiniest forms of matter, suddenly people are asking, well, what happens when the universe itself was about the size of an atom or not that much bigger than a city? The energy scales that are needed are the energy scales of particle physics. And so you have to marry the 2. And so it was in that time that then people thought, well, if in those very, very early times, a millionth of a second right after the Big Bang, the energies are so high that atoms could not exist. And so that's some of the things that we'll talk about in some of the next clips, but we'll get to that. But that's just kind of the idea that indeed the quarks that we study when we go to the very small using particle accelerators are deeply connected to what was the structure of the universe in the very, very early times. And so to me, those kinds of connections are also some of the things that blow my mind, that you start studying the very small or you start studying the very big, and there are parts in which they connect, in which you need both of them in order to understand what is happening. So that's some of the things that we wanted to convey in the film as well. And it was always a lot of fun having these kinds of discussions with Stephen as to like, okay, what are we going to do? How are we going to portray this? And how are we going to convey this?
I'll tell you, I really struggle with color, because that doesn't, like, there can't be color at that scale. And so
yes.
so did the designers say, well, there's no color. You can't have color. Color is a photon. It's not a nucleus of an atom. So,
well, that's some of the questions that we're getting coming in are, you know, what is this what an atom actually looks like? Is it, you know, what's the relationship between the visualization that we see and what we know about reality?
So that's a good question, and that's something that indeed we discussed at length, because the idea of color is just, as I mentioned, it's a useful mnemonic, but visually we use it because, you know, it helps us remind us about this mnemonic. We don't think that that's how atoms actually look like, because when we say how they look like, again, as Stephen just mentioned, we need to talk about light. We use our eyes to see, and so when we say how things look like, that's what we're used to. But these things are so small that regular visible light the wavelengths of visible light are way too big. And so there's no such thing as real actual color, like, you know, red color has a particular wavelength, green color has a particular wavelength, and so does blue. But all of those wavelengths are too big compared to the size of a proton, much less the size of a quark. So they're just simply there as a mnemonic. And to make things even more interesting and more kind of, to me, mind-boggling, one thing that I talked about with Stephen, and it was not easy to get into the animations, but that can be kind of seen in this sort of animation, is that the color itself, or at least whatever charge, I mean, we call it color, but it's really the charge that quarks carry, is something that is actually exchanged when quarks interact. And that's something that we had never seen in nature before. All the other forces that we're used to, like gravity, which is familiar, and even electromagnetism, which is difficult but also familiar, because we can, you know, turn on a light and we can understand that, yeah, these are electrons traveling through a copper wire that are, you know, doing something, and therefore we see, you know, our lights turn on. But the electron, when we start going again back to the basics, like how do electrons interact in a hydrogen atom? We see an electron kind of orbiting a positively charged nucleus, and the electron has negative charge. And so we see that there's these two kinds of charge, positive and negative. But the electron always keeps its charge. The electron is always negatively charged. That's one of its defining properties. So when it interacts with a proton, the proton is always positive, the electron is always negative. They always keep their charge. But these quarks don't. The quarks, when we say like they have red or green or blue color, when they exchange the particle that exchanges a force, which in the case of electromagnetism, it's a photon, the photon doesn't carry charge. And so a proton interacting with an electron via the exchange of photons doesn't change the charge of the electron or doesn't change the charge of a proton. But for the case of quarks, the particle that is the analogous particle to the photon, which, because it's the strongest force, and again, we have to invent names for them, and we think of this as the strongest possible glue, we call that particle a gluon, then it turns out that these gluons actually do carry charge. So the quarks themselves change color. They change their charge as they interact, which would be the equivalent of having an electron that we see at one point being negatively charged, and then an instant later have a completely different charge, not negative, but maybe positive. We've never seen that. It doesn't exist in our universe. But quarks do that. Quarks do that for that particular interaction. So that's also why it's so kind of mind-boggling to explain. It's just things that we are not used to seeing in the more familiar forces like gravity or like electromagnetism. So that's part of what makes it so hard to have to try to explain some of these some of these issues, because these are things that we're really not used to seeing visually. And so this is some of the best things we can do. And we took definitely the idea of color and just portray them with color, even though we know that's not exactly how they look like. But it helps us at least to visualize, to have some concept, because some of these concepts are just so difficult to understand, simply because we're not used to playing with them. We're not used to seeing them in our everyday lives.
Great. I also have a question here about what are quarks made of?
Very good. As far as we can tell, quarks are not made up of anything smaller yet. That doesn't mean that they aren't. It just means with the limits of our technology, as far as we can tell, quarks are the idealization of the atom that the Greeks thought, the unbreakable, immortal things. The particles that, as far as we can tell, don't have an inner structure. The electron, for that matter, also is one of them. As far as we can tell, an electron is not made up of yet smaller things. So, and so we've identified a few of those. It turns out that there are 6 kinds of quarks. And so it turns out that just 2 of them are what's needed to make you and me and everything that is making up the periodic table. So when we realized that there were more of them, that was pretty strange. And so it turns out that that first quark that was realized was new, was given the name the strange quark, precisely for that reason. And so again, we had to give names in such a whimsical way because we were inventing language for things that we didn't have a concept for. And yet nature was telling us, by the way, there's these quarks and you start with 2 of them and you can make up the entire periodic table just using 2 quarks and an electron, which is a huge simplicity. So again, talking about simplicity, there's hundreds of elements in the periodic table. You can get all of them just with 2 quarks and 1 electron. Just combine them in different ways and the entire periodic table comes out. Yet nature saw fit to have more than just 2 quarks. So that was strange. So the first one was called the strange quark. And then we end up having actually 6 total quarks. We don't know why. Why are they 6 quarks? Nobody knows. Nobody knows why they're 6, because we don't necessarily need them for a lot of things in our everyday lives, but they are there. And so that's part of what I study. I study some of the heavier quarks, which have some whimsical names like charm and beauty. So I always like to tell people when they say, what do you do? I study charm and beauty. So that's part of what I do.
Great. Okay, I think we should probably move on to your next clip.
So yeah, we're getting now inside the collider. And in a very true sense, the collider is the coolest, the biggest, and emptiest thing that we've actually ever made, in a very true sense.
Inside these 2 vacuum pipes will travel beams of particles going in opposite directions and accelerating to near the speed of light before we smash them together. Each section of Large Hadron Collider pipe contains very powerful magnets. They keep the particle beams perfectly aligned to collide with each other, we hope. The Large Hadron Collider is in effect a 27-kilometer superconductor. The pipes are also held at a very high vacuum, emptier than interstellar space.
And I like this scene because Stephen had us, so several of the people that you see here are some of the students in my group. And when I still talk to the students in my group about some of their fondest memories, many of them still say that, you know, coming here and at CERN and working with Stephen and making the film was a total blast. So I always like the fact, so several of the people that are here in this scene are some of the students that are working in my group. And going a little bit back to the questions about the collider. So part of what you can see here are some of the workings of the collider. So the big tube contains these 2 vacuum pipes, and the beams of particles are going in one direction in one vacuum pipe and in the opposite direction in the other vacuum pipe. And then these green lines that you see here represent the magnetic field lines of the magnets that are encased in these big tubes. So essentially, each of those kind of big blue tubes that you see here that are part of the beginning of the scene, like this blue tube that you see here, they're essentially the main component that each of them have is a huge magnet. And there's some of the most powerful magnets that are that we're able to make. And the facility where we were actually filming this is actually a test facility for trying to make even stronger magnets. As CERN is trying to push the envelope in making stronger and stronger magnets, because that would allow us to make accelerators that would reach even higher energies. But some of the very powerful magnet techniques, to go back to another of the questions regarding possible applications, again, this has medical applications, because if you ever have taken an MRI image, the MRI machines need very powerful magnets. And so the other places where you can find such powerful magnetic fields are, again, in hospitals, in MRI machines. And if we're able to get technology that gives us even more powerful magnets, then we would be able to make MRI machines that would be a lot more, a lot smaller and more portable, and we would be able to take them out into different areas that would be not feasible right now, because you'd have to have this humongous room to house the magnet to have the MRI machine. But if we're able to make them more portable, then that would also be a huge boon. So that's another potential application.
We have a question in the Q&A about whether it's true that protons and neutrons also can switch their identities by the exchange of mesons inside the nucleus.
Yes. So that is certainly something that can happen, and that's part of how the strong interaction works at the nuclear level. So inside a proton, if you just have a proton, then the nuclear interaction is working at the level of exchanges between the quarks. But when you have a nucleus, and basically one of the ways in which we can think of why a nucleus is stuck together, because if you think about it, you have lots of protons that just have electric charge, positive electrical charge, and neutrons that are electrically neutral. So if there was nothing but electricity, the nucleus would not exist. Atoms, as we know them, would not exist. And so, indeed, in order to keep the protons stuck together inside the nucleus and the neutrons stuck together, you need a new force. And it is that strong force that, that's why we call it a strong force, because it is much stronger than electromagnetism, which is pretty strong already. And so that's why we say that the strong force, the strong nuclear force, is the strongest of all the forces of nature, because it can overcome the electrical repulsion between protons, and it keeps the protons and the neutrons stuck together. And one way in which we can understand how that exchange can happen is, as was mentioned in the question, via the exchange of particles called mesons. That are also made up of quarks. That's why it's part of the strong interaction, that are being exchanged back and forth, just sort of like two players that are constantly exchanging a basketball, say, and that keeps them interacting and keeps them sort of stuck together. So, when, depending on the type of meson that they exchange, it is possible within a nucleus to exchange the identity of a proton to a neutron. But the overall balance of the number of protons and neutrons stays the same. But an individual proton or an individual neutron can actually switch their identity by exchanging a pi meson, indeed.
So we also have a question about, is there a particular reason why the collider is so huge? Couldn't it be small with powerful magnets?
That's a very good question. It could certainly be made smaller if we had more powerful magnets. But these are the most powerful magnets that we are able to make. So, so that's why it's as big as it can be. So we're essentially already pushing the envelope, and essentially we pushed the envelope in some sense a little bit too much. At the very beginning of the life of the Large Hadron Collider, actually there was a design flaw in some of these magnets, and that led to an explosion. This happened around 2010 or so. And that set the program back about a year. And basically since then, the accelerator hasn't actually gone up to the design field that the magnets are able to sustain. It's only going to be after that shutdown that's happening right now that we hope to get the magnets up to the field and the particles to the energy that the LHC was originally designed to have. And so that's essentially been 10 years after the LHC actually started. And so partly because, again, the magnets were not able to sustain those high fields. And so they had some engineering issues with that we're still trying to solve. And so that's why this facility is there. It's part of what, when we were there, I remember Stephen and I got a tour of the facility, and we were being told like some of the things that they do there. And I thought it was really cool because they essentially, in that facility, they basically push the magnets to their limit. They essentially get them to explode in a controlled way. So they basically had like a huge container that was able to withstand an actual explosion, and then put the magnets in there, cooled them down to almost absolute zero, cranked up the field as high as it would go, and then go even higher to see when the magnet would essentially just explode. And so that's what some of the experiments that were actually happening in that facility with where we filmed that scene. So that was pretty cool.
We have some other questions that I think will set you up for your next clip well, which is how do you actually get things to collide? And what does that look like?
Yes, that's a very good question. So I think some of this, and if not this one, some of the next one, is basically about how we smash the nuclei and how we get them first to accelerate and then to collide. So that is indeed, I think this might be about.
We're going to try to collide massive lead ions, atoms with their outer electrons stripped away, 200 times heavier than earlier experiments. We will accelerate these lead ions to the highest energies achievable on Earth, passing them from one accelerator to the other, each one increasing the energy of the ions. When they enter the largest accelerator ring, they will be traveling so fast, they will be a hair's breadth from reaching the speed of light.
So hopefully that gives you some idea as to how we get them to collide. Part of it is, it's actually done in stages. So when we were discussing this, I remember, Stephen, that you said, wait a second, does that mean that we're essentially going through the entire history of particle physics while we're at CERN? Because each collider was the highest energy collider of its time. And so, Stephen always has this vision of like, what's the good story here? And indeed, it's right. Many of these were the state-of-the-art accelerator in the 50s, then the 60s, and the 70s, and the 80s. And so we're basically going through the whole history of particle physics every time we accelerate one of these ions. So there's many accelerator facilities, and they're all interconnected to each other. Actually, when I first got to CERN, this ring here is where I first started working, and that was the highest energy accelerator back in the 80s. And so when I got to CERN in the 90s, there already was the big ring. It was not the Large Hadron Collider, but it was an electron-positron machine that was in the ring. But they were using this machine to collide heavy ions, which is how I got started in that field. But the accelerators are still being used for many, many different studies. And as we accelerate them into the Large Hadron Collider, we basically pass through many of the various stages that were the biggest accelerator of their day.
So I have a question for Stephen, which is how much knowledge about this subject did you have when you started this, and how much research was necessary to be done to make the film, and what was the coolest thing that you learned?
I guess not much knowledge to start with, which is in a way it's a good thing, because nor does the audience. So I kind of on that side of the spectrum between Manuel and I can only say we had so much fun together. I just, sometimes he'd give me a headache I'd have to go and think about things really carefully. But it was always really fun to learn. And again, I think because of the simplicity of the science is monstrously complex, but it's also profoundly simple. And we won't see that in on these clips, but the other side of the story is, you know, if we're making a film about the simplest thing in the universe, what about the other simple things in science? And many of the great epic breakthroughs in science were very simple things that kids can understand. You know, boiling water for Pasteur, and he found that life was not spontaneous, that it doesn't restart, you know, which has really profound implications to astronomy and everything. And Leeuwenhoek, one of the things that I loved about the film was I had this idea that, you know, the microscope was something that kids have at school. There's something they can play with. They're not that expensive. It really gives them access. But I wasn't sure if CERN was a microscope, and I was so excited when Manuel said, and the other scientists said, yeah, sure, it's a microscope. Of course it's a microscope. So there's another window that, you know, kids can relate to this amazing thing. And at the same time, you know, you could go to Leeuwenhoek and look at the beginnings of science and bacteria and understanding of pathogens and medicine. And again, for me, it was a search for those simple milestones in science that if I was a candidate for this, if I was one of the Manuel students, you know, here you are going to Switzerland and at the, you know, center of science, really. And right down, you know, over in Italy, there was Galileo, and just, you know, in that neighborhood is the history of science. And I thought I was really something that anybody going to CERN would be wondering about the other things. And there was a moment in the bar when we were filming in the bar. There were pictures of what was it? I think there were pictures of
Einstein and Chaplin and yeah.
And Chaplin, yeah, that's right. And I was amazed that the physics students didn't really know Einstein's appearance. You know, they knew Chaplin, but not Einstein. And then I said, well, what do you think the greatest scientist of all was? And I thought they would say Einstein. They said Darwin, which fascinated me. I'm kind of running all over the place, but they all agreed that Darwin was the great scientist and one of the greatest scientists. And again, it's simple, you know, evolution. If you arrive from outer space, there's two things you'd want to, not outer space, but from another universe. You'd wonder, okay, how the sun is burning or the stars are burning. And that's kind of Einstein. And then, you know, somebody walks up to you, well, how the hell did that happen? Well, that's Darwin. So between the two of them, you know, that's the history of science. I'm simplifying it, obviously. Anyway, did I answer any of the questions? Maybe not.
I think you did. I have a question, Manuel. How are the ions produced and inserted into the accelerator?
Yeah, so how? So I think depends on the ion species. For example, like simply go back to what Stephen usually starts with. What's the simplest one? And for the simplest one, when we do hydrogen, we start from a hydrogen gas bottle, and we then ionize it, which is just simply means we take off an electron, and we do that just using an electric discharge. Then we use the electric fields to send the protons down the vacuum pipes. But that's how it starts. It starts from kind of a simple gas bottle. And depending on the material, if you're able to have a gas, then you can start with that. But in other cases, you might start with just a tiny piece of solid material, which you can then heat up and evaporate. But it doesn't take that much, because sometimes, like for example, in one of the accelerators that I also work in the US, in Brookhaven National Lab in New York, the ion species that we use is gold. And people are like, well, how much gold do you need? And you know, people sometimes imagine that you have like this, you know, Fort Knox type, you know, piece of gold just lying around. But it turns out that for, you know, we've been running the accelerator for 20 years, and you need, you know, a tiny fraction of the amount of gold that's in a gold ring to keep the accelerator going, because again, we're colliding things atom by atom. And the amount of atoms that are in a tiny gram of gold is orders of magnitude, like thousands and thousands of times bigger than the amount of atoms we need to run the accelerator for a decade. So it's really just tiny amounts that are actually needed regarding human scales, but there's billions and billions of atoms that in those tiny scales for us happen to be, again, just because the atoms are so tiny. So, but it usually starts with something like a gas or a tiny piece of metal that you can then evaporate and then ionize, and then start using the whole machinery of electric and magnetic fields to send them into the accelerator.
Great. All right, I think we probably should move on to your next clip.
Mm-hmm. So, yeah, so here is where this is, I think, a short one. This is where we start introducing the idea that we're actually going to try to get into the proton, and not just into the proton, but get hot enough to melt the proton.
When two of these tiny giants collide in the CMS detector, we expect a temperature 100,000 times hotter than the sun. A quest to understand the microcosm. A journey that began centuries ago.
So that was a short clip, because that one introduced the idea, and that's why we have this visual of something that looks kind of like the sun. Because, you know, as Steve and I were discussing, like, what is this plasma? What does plasma mean? The most familiar plasma for all of us is the sun. The sun is a state of matter that we call a plasma. And so when we think, what do we mean by states of matter? The more familiar ones are things like a liquid, a solid, a gas. All of those are different states of matter. And for us, a familiar substance like water can exist in all three. And so we know that if we, you know, put something in the freezer, it turns water into a solid. Then at room temperature, it's a liquid. And if we, you know, put it in a stove and start heating it up, it becomes a gas. And all of those are still water, but they're in different physical states. But to change the different states, all we are doing is changing the temperature. So then we can then start thinking, well, what does temperature really mean? Ultimately, temperature is a measure of how much energy the particles that make up that substance have. In other words, how fast are they moving? How fast are they jiggling? The faster they're moving, the more energy they have, the higher the temperature. And so a solid, they're not moving around very fast. They don't have a lot of energy. And so they just kind of stay put, which gives its solid its rigidity. But as you start making them move faster and faster and faster, well, then if the particles are actually moving around so that they're not staying put, that's what gives a liquid its fluidity. And if you make them move even faster, you can get, you know, them to expand even more and become a gas. But if you get to temperatures that are high enough that at the atomic level, they're moving so fast that if they meet each other, they collide so violently that you rip apart the atoms, or rather the electrons from the atom. That's what's a plasma. That's what a plasma is. That's what's happening in the sun. The temperature is so high in the sun that the particles are moving so fast that the electrons are ripped apart from the atom. It's hot enough that the atom melts. So what we wanted to do was to go even hotter. And that's why you mentioned there. To melt the proton, we needed to go 100,000 times the temperature of the sun. So to me, that always still boggles my mind, because we think of the sun as essentially something that is so hot that you touch it and you dissolve. Well, now for what we're trying to do, the sun is too cold. So that's why we had to go back there to not just something that exists in our current universe, but something that existed only at the very beginnings of our own universe, when the temperatures were the hottest that they've ever been, essentially. and where things like the sun were too cold. And so that's what we were trying to do. Nobody had, realized, like, is this something that really existed? Again, a lot of this was speculative back in the 80s, but now we're actually able to put hard science on some of these seemingly fantastical notions. Can we melt the proton? So that's essentially what we were trying to do. Melting a nucleus, melting an atomic nucleus, melting a proton, melting a neutron, to free up the quarks inside. That was the idea. And again, that was, what Stephen was mentioning. She was like, if you do that, you're able to liberate this very simple primordial particle that was the simplest one, that now in our world looks complicated. But if we go back to the beginning, everything was simple because everything was quarks. And
so, are you going to show the collisions?
Yes, I think that's in 2 more clips. I think that's
okay.
it. So I have like 1 clip that just shows the detector and then the collisions.
Oh, good, because I got a silly story before that.
Yeah.
Or after.
Mm-hmm. So Gretchen, I don't know if there's any questions. I think there's just 2 more clips. One on the detectors, to just show the detectors, and then we can show the collisions.
Sure, it sounds good. I have one question here, which is, how much electrical power does the collider use when it's running?
Yes, that's a good question. I think once we did some estimates, just because that's a very interesting question that we ourselves also ask ourselves. And when the accelerator is running, it draws as much power as, I think, about 1/3 of the city of Geneva, because Geneva is the kind of closest reference. So it, as much power as you need to power the entire city of Geneva, about 1/3 of it is the amount of power that just the collider takes. So it's not as much as saying like, no, you need much more than the city, but it's still pretty sizable. Saying like 1/3 of the size of a city just for one machine, it's still pretty big. So that gives you an idea. It's not unheard of, but it is pretty big. I mean, and to make this machine, another thing that you can think about is, in order to build it, basically the entire planet kind of chipped in order to make the machine. And so, and the scientists that are working there and the engineers that are working there are coming from essentially all over the planet. So it really took a worldwide effort to build the machine and to tease out the science that is coming out of it. So I didn't have a clip specifically about that, but that's something we also did when we were talking about it, about what other stories we wanted to tell. I think we did want to have, and we tried to showcase some of that, showing how international the whole thing is, because it is ultimately all of humanity kind of working together for a goal that is, has nothing to do with making money or selling a product or something. It's just the ultimate goal is to further human knowledge. And there's not a lot of places where you can still say that all of humanity comes together for the greater good of all of us. And so that we did have some of that in the movie. I didn't have a clip about that, but I think I certainly liked that. And when we communicated that to Stephen was like, yeah, we should interview as many people from many different languages and as many cultures as possible, and kind of really show how international this whole thing is. That was definitely part of the goal.
Great. Okay. Well, let's see the detector.
Right. So, so the detector, and I want to emphasize that sometimes I see the detector that, it's kind of what you can see behind me is a picture of the detector. But we had this really nice visual of what happens when you actually close the detector as we were getting ready to take data. And hopefully one of the things that will happen when we're able to return to see it in the big screen is that the detectors are as big as an IMAX screen. That's in a Zoom webinar. I really hope that pretty soon we'll all be able to do that, because there's nothing like that.
In 3D.
In 3D.
We're about to fire up the greatest time machine in the history of the world, becoming time travelers, going back further than ever before, to within a millionth of a second from the beginning of the universe.
So that kind of, again, shows just the scale of how big these things are. So these things are 5 stories high, and that's about the size of the IMAX screen.
I will say these are entirely computer graphic. So we built the entire room, this particular experiment, the Atlas.
CMS.
CMS, I'm sorry. CMS, in complete, absolute detail. So one day we're going to do a VR show because we own this entire room. And so we can actually have people walk around inside it. But this is because it was very hard to actually film in real time the kind of thing opening and closing, and it would be a lot slower than this. So we undertook to build the entire thing. It was kind of months of work. But there you go.
And it's definitely one of the nicest visuals as well. And I'm definitely also looking forward to getting the VR experience, because that's something that you can, being able to, not everybody can have a trip to CERN. And even if you have a trip to CERN, when the accelerator is going, you can't necessarily go in and see it, but having the experience of really seeing how big these things are and being able to explore it, having that in VR is going to be amazing.
Do you have to clean the collider after every experiment to avoid having residual particles fly around, or?
So usually, like, what might happen is not so much that the particles that are flying around, but rather the high amount so the particle collisions basically are essentially radiation. And so there's protons and neutrons and lots also particles flying around, which can then interact with the material of the detector. Particularly, the closer the material is, the more that they will interact with it, and so the more radiation damage that they might have. And so one of the reasons why we are doing the shutdown now is that so that some of the material, for example, some of the silicon detectors that are very, very close to the interaction point, they can be replaced with new ones to prevent aging from radiation damage. So, but that usually takes a few years. And so the accelerator has been running for 10 years. And right now, this is when we're doing this kind of big shutdown and an upgrade of the detector components. And then after 10 years, usually, like, the technology has improved, so we can actually put in better detectors. So that's a process that is ongoing.
How frequently is the collider operated?
That's a good question. So because it's, as you can imagine, so it's just such an expensive undertaking, and it's a to when you're looking for things that are so rare, like discovering a new particle or something like that, when you run the accelerator, you basically try to run it as much as you can. So typically the accelerator runs 11 months out of the year, something like that. And when it's running, it is running, if possible, 24/7. So we have to have shift crews at the accelerator and at the detectors that are there 24/7. So sometimes, for example, when I send my students out to CERN, if they're there for a year, then they are some of the people that are sitting on shifts. Like when I was at CERN for a year, I was also sitting on shifts in the control room and taking data. And everybody, when you have a collaboration like CMS of 3,000 people, all of us have to come together and help with the data taking. But yeah, it usually, when it's running full on as much as you can with as little downtime as you can. But then, at some point, usually during Christmas time or something like that, then the accelerator shuts down because, the people also need to have a holiday. And so, but if possible, you're running about 11 months out of the year. And for the experiments that we're running, we usually run 1 month of data with heavy ions in the machine. And so 11 months, so that's 10 months roughly with protons, 1 month with heavy ions typically.
And then I also have a question here about what material is the collider made of?
Well, there's several different things. I mean, you saw like the magnets, for example, are I think superconducting magnets. So I think they are I think niobium magnets. I think. But there's all sorts of materials, like in, you know, the detector itself might have silicon components, might have some of my favorite materials in the detector. For example, there's a detector that is used to measure electromagnetic energy. And it's basically a crystal that's about this big. And well, not a crystal, it's thousands of those types of crystals that are all kind of arrayed together. But the crystal is made of lead tungstate. And the cool thing about that is that when I'm used to seeing lead is like a metal that's gray and opaque. But if you have lead tungstate, it really is a crystal, like a transparent crystal. So you see this thing that looks kind of like literally out of a movie, like Superman, like, you know, these crystals of like the ice fortress of Superman. That's how it looks like. And it's about this small, but because it's made of lead and tungsten, which are very dense materials, you try to pick one of these things up and it's super heavy. So, so there's some really, really cool materials that are part of the detector components. Another part of the detector is actually made of brass that was actually, a lot of that brass was molten brass that was coming from World War II artillery shells, which I really like that kind of story because it's kind of like technology coming full circle, technology that was first used for war being repurposed for the purposes of serving science and serving humanity instead of trying to kill each other. So, so I really like that there's some repurposed artillery shells that are now having a second life as material for the for our energy measurements in the detector here.
Great. All right, I think we're ready to see some collisions.
Sure. So this is one of the probably my favorite sequences where we finally actually get to see the particles collide.
Just as quickly as it started, it's over.
So as on the previous
Oh,
page.
the one with no loops, right? Yeah.
Before the collider has even stopped, the chant begins. Did you find anything? I think it's fair to say we found everything. Exactly what the collider was built to do. The experiment has proven the theory of the quark-gluon epoch. A lost world, a millionth of a second after the Big Bang. We were not prepared for what we found next. 7 million miles across, with a temperature 1 million times hotter than the sun. We found a strange plasma, more liquid than water, held together with the strongest force in the universe. A boiling cauldron of tiny immortal quarks, the purest form of matter possible. A perfect fluid, waiting to form the universe to come.
So I have a few things to say.
Well, please.
Can I say something? You know, it's sort of the ultimate challenge because none of this exists. So the only thing you really know about is that each collision is different. I mean, every one of them, because of the trajectory, because of the way they glance, they hit each other, that it's a completely different thing every time. But after we had some screenings, you know, people would come up to me and say, well, dude, there's no sound in there. And I say, yeah, dude, but there's no picture either. So what do you want me to do as a filmmaker? I mean, it's quite cheap to have neither sound nor picture nor music. We could have, you know, none of those things are really accurate. But on the other hand, it's, you know, for the artists and for the sound mixers and sound people, it's just fun because it's anything you want, really. Is that fair to say?
Yeah, definitely.
It has to be fun, you know, it has to be exciting. And so, but again, you don't see or hear any of these things. They don't exist in our senses. So it's a wonderful challenge, and especially 3D. These things are, you know, exploding in the theater and flying around your face, and it's a lot of fun.
Yeah, and probably I mean, the idea that you're able to get people excited by thinking about, yes, we're actually colliding and producing new particles, and nobody really knows exactly how it looks, because you can't say that it would look any particular way, as right. Stephen says. It's a chance to let all of our imaginations fly a little bit as to what is happening in that you know, tiny instant when these things are flying out. I mean, and some of it, when we were coming up with how it might look like, or how, you know, just to inspire the artists. I remember talking with Stephen, and, you know, something I can share here, that we do have in our detectors a way to look at the data, like, you know, meters away from the collision, as to what the detectors actually see. And so these are some pictures of attempts at visualizing what the data actually look like. Where, for example, these blue towers that you see here, this blue kind of prism-like things, are represent the energy that in a particular region of the detector is actually measured. And the red ones are the same for a specific kind of energy as well. So all of these are just telling you where the energy is actually going. And then this, the region here that is in yellow is meant to convey the information of the tracker detector, which is the detector that traces the tracks of the particles that are flying out in three-dimensional space. So we're able to see that, but this is now meters away. And so, you know, if I show this another picture, then again, these are now in the scale where these are things that are measured in the actual detector. But what is happening, you know, in the atomic scale, nobody knows. And so these kinds of visualizations, you know, really do convey that there's a, you know, huge number of particles, thousands of particles that are flying out in one single collision of a heavy ion, which is why it makes them so spectacular. And you can, based on that, try to then imagine what that might be, and that's what the animators tried. And I really like some of the results that they came up with that were pretty whimsical. For example, like the ones with the balloons. I particularly enjoyed that one. Let's see if I can get to that frame. So I mean, some of those very much look like what you expect, but this one, we actually have animations from theoretical calculations that look very much like this. But in this particular case, when they convey, like, okay, there was all these quarks with all these colors, someone decided, yeah, let's throw in some balloons in there. And it works really well, because it's not that different than what some of the very sophisticated theoretical minds in our world came up with. And so that you have these heavy ions passing through each other, and in their wake, you get this field of gluons and quarks that are all colorful. And what better way to represent that with just colorful balloons that are flying around? And so, so some of these are just, I think are fantastic.
That certainly are beautiful to see what that looks like.
Yeah.
So I have a couple questions to kind of close us out, and I apologize to those of you who asked questions we didn't get to. There were over 100 people on here at some point during the talk. But a last question for you, Manuel. So a number of questions have come up over the course of this about what else might we be able to detect using colliders? Like, could we determine whether or not superstrings are there? Could we detect gravitons? Like, what else might we be able to find with colliders?
That's a good question. And that definitely, a lot of my colleagues are working very hard at trying to find evidence for new physics at the Large Hadron Collider. Just some things that I think might, I hope we might be able to see in our lifetime. One would be, and we don't know that we really don't know it. We could get lucky, and maybe in a machine like the LHC, we would see it. Maybe in the next one, a dark matter candidate particle. So a dark matter is something that we know for, again, it's a connection between astrophysics and hopefully particle physics. We have evidence from astrophysics that as we look at how stars are orbiting galaxies, or how planets are orbiting stars. So typically, I think the first evidence came from the rotational speed of galaxies. And when people would look at the visible matter like stars, they realized that they were moving a lot faster than would have been indicated just by the gravity from the stars. And so people then came up with the idea, maybe there's additional matter that we don't see. So we called it dark matter. And this all started in the 1930s, and decade by decade, more and more evidence has been coming through. And nowadays, there's essentially nobody that doesn't think that there isn't dark matter out there, but nobody knows what it is. And so one potential thing that the LHC can do is find particles that are not part of the particles that we now know, anything that makes up the periodic table, or anything that makes up these quarks and these 6 types of quarks, in fact, that it would be a completely new type of particle. That might then be a candidate for the dark matter that we know might be out there. So it could be particles, it could be something else. But if it's particles, it might be that the LHC is able to produce such kinds of particles. That's one example. And like that, there are many other things that the LHC is trying to do. So to touch a little bit on the mention of superstrings, I don't think that we'll be able to directly detect superstrings because the natural scale for superstrings is so unimaginably small. So we're already, quarks are pretty unimaginably small for us. But there's about as much difference, if not more, between the scales of humans and quarks and the scale of quarks to superstrings. So that's how far away superstrings are. And so with the technology that we have, there's simply no way that we would ever be able to directly probe and see whether quarks are actually made up of strings. However, we can indirectly probe consequences of whether strings exist, because strings need many dimensions in order to exist. And what we mean by that is that some of the theorists say that we must live in a universe that must have something like 11 dimensions. However, as far as we can tell, we have 3 dimensions of space and 1 of time. And if there are more, we haven't seen them. But one of the things that the LHC is trying to do is to look for evidence of some of these extra dimensions. If we find evidence for those extra dimensions, that would be mind-boggling, because that would indeed revolutionize our notions of what space and time are. As far as we can tell, as I mentioned, we think that we have 3 dimensions of space and 1 of time. If we have more, that would be a completely revolutionary discovery. Of course, we haven't found it yet, which is why you haven't read it in the papers. But if we're able to, if we find something like that, I'm pretty sure that it'll be plastered in every news outlet everywhere. We just haven't found it yet. But these are the kinds of things that the LHC is also trying to find.
Thanks. And Stephen, a last question for you. Manuel let it slip in our pre-show warm-up that he wasn't originally supposed to be the narrator for this film. Can you talk a little bit about what made you decide to change your mind on that standpoint?
Well, normally we have a narrator and a voiceover, what I call voiceover, which is a character voiceover. But Manuel was so good at, his voice is so spectacular. And character voiceovers are always better because they bring, the real person, the real storyteller to the table. And so I don't ever like to say, you know, you're gonna narrate the film in case they can't do it. A lot of people just can't do it, period. They just can't read naturally. But Manuel was a natural, and he does a beautiful job. So it was, anyway, it was a great pleasure. A lot of fun working with Manuel, and I learned an enormous amount, and it was just fun. But you don't have time to run the ending, Manuel, because I like the ending where you go off on the snowboard.
Right. Yes. I didn't put that in one of the clips here, but yes, one of the things that when we were discussing what to include in the film, and that, you know, as we're telling a story, Stephen asked me, well, you know, what do you do besides physics? What else do you do for fun? And so I told him, well, you know, I like splitboarding. And so as we kind of explored that, Stephen was like, well, you know what, we should put some of your splitboarding in the film. And so I ended up shooting some footage with a GoPro, and then there's other footage that is not me, but it's part of what splitboarders do. That is also part of the film, which I think is also a really neat thing. And as Stephen mentioned, the way we end the film, we actually start the film and we end the film talking a little bit about snowboarding, and kind of like showing some scenes where I'm actually snowboarding. So that's, so I really enjoyed that.
Well, more important though, you get to the final lines, and
right.
When you come to the end of science, you kind of have to go into philosophy, and it's actually something that maybe all fathers tell their children, but my dad told me, and I included that as if it's Manuel's family, but in the end, you know, science can only bring so much meaning, and we'll never know what the meaning of life is, but in the end, life has the meaning that you give it. And Manuel goes off on the snowboard in the end, and I think it's a great ending.
Yep.
Finding meaning in a snowboard
yes.
instead of the collider.
Mm-hmm.
Well, I'd like to thank both Manuel and Stephen for spending this afternoon with us. I see that a couple of people asked whether or not the tech will be showing this film in our IMAX theater. We are certainly looking into that. We don't really know what our IMAX schedule looks like, as we don't really know what our reopening schedule looks like yet either. But thank you so much, Manuel and Stephen, and all of you for attending. We really appreciate your support of the tech, and please check your emails to see what other upcoming events we might have coming your way soon. Thank you all.
Thanks, Gretchen. Appreciate
Thanks, Gretchen.
Great fun. Thank you.
Great.